Hello and welcome. In this video, I want to review some important deep learning methods for pose estimation. I try to make a simple representation of the models using TensorFlow. Finally, I show a fast, state-of-the-art approach. First, I start with the paper DeepPose Human Pose Estimation via Deep Neural Networks, which was one of the first models to show that deep learning could be successfully applied to human pose estimation. Let's review its model. We have an RGB image as input, followed by a convolutional layer with 96 filters, a kernel size of 11, stride of 4, same padding and ReLU activation function, resulting in an output of 55 by 55 by 96. Next, we apply local response normalization. LRN is a technique used in such neural networks to normalize the response of each neuron to its neighbors. It considers a neighborhood of channels around the current channel and normalizes the response of the current channel based on the squared sum of the responses in that neighborhood. LRN was commonly used in earlier algorithms, but it has largely been replaced by batch normalization. After this, we have a max spline layer with a pool size of 3 and a stride of 2. This pattern is repeated with different filter sizes and configurations. After the final max spline layer, we flatten the output and pass it through two fully connected layers, followed by a dropout layer. The output is a fully connected layer with 32 units corresponding to 16 body parts. This means the model is mapping the pixel values to joint locations in a regression-based manner. The key implementation of this algorithm is that after the initial stage, when we have a rough estimate of joint locations, the network creates a patch around each predicted joint and feeds this patch back into the same network to refine the joint location. By doing this, the network can iteratively focus on areas of interest in the image. It crops and resizes these patches back to the original image size, allowing the model to zoom in on the predicted joint and refine its prediction. The loss function used in DeepPose is mean square error, which is typical for regression tasks. It calculates the distance between the predicted joint coordinates and the ground truth coordinates. Here is the TensorFlow implementation of the model. We begin with a convolutional layer using 96 filters, followed by local response normalization and a max spline layer. The remaining layers are implemented accordingly. Finally, we have a fully connected layer with 32 outputs, which represent the location of body parts. Below is a summary of the model and a visual representation. The next model I'm going to discuss is the Hourglass, which was presented in paper Stacked Hourglass Networks for Human Pose Estimation. The name derives from its hourglass shape when visualized, which reflects the model's structure of downsampling followed by upsampling. Initially, the model uses convolutions and pooling layers to reduce the spatial resolution of the image, allowing to focus on larger scale features. This is because stacking more convolution layers expands the receptive field of each neuron. Each layer builds on the outputs of the previous one, capturing increasingly abstract features. Pooling layers further decrease the size of the feature map by summarizing information over small windows. This compression reduces spatial details, but allows the network to see larger regions of the input image at once, providing a global layout of the image. After downsampling, it uses nearest neighbor upsampling to bring feature maps back to their original size. This larger representation allows the model to analyze the same features at a higher resolution, which can improve its ability to make precise predictions. The complete architectures consist of stacking multiple Hourglass modules, each of which refines the key point predictions made by previous Hourglass. A crucial aspect of this model is the use of skip connections or residual connections. These connections enable the model to combine the global features extracted during downsampling with high resolutions retained during the upsampling process. This helps the model accurately detect body parts and reduce the risk of losing important detail throughout the downsampling phase. As described in the paper, we first apply a one-by-one convolution to reduce the feature maps to 128 channels. Then a 3x3 convolution is applied, followed by another 1x1 convolution to expand the feature maps to 256 channels. The input is then added to the output through a skip connection. This is a standard implementation of a residual block where we first compress the data, extract features, and then restore the data depth to its original form. Before entering the Hourglass, the paper first applies a series of convolutions and max poolings to reduce the image dimension. We begin with a count to the layer that has a stride of 2 and a kernel size of 7x7. This is followed by a residual block. After this, max pooling layer is performed to downsample the output to 64x64. Before entering the Hourglass modules, 2 additional residual blocks are applied. Next, in the Hourglass module, we specify how many times we want to downsample the input, applying a residual followed by max pooling layer. We also store the outputs of the residual blocks for later use in the corresponding layers during upsampling. Before the upsampling phase, we have another residual block. Then we upsample the output using the nearest neighbor upsampling. As the paper used this method, we can also use transposed convolutions. During upsampling, we add relevant outputs from the downsampling path. So let's write stacked Hourglass network, where we specify how many stacks we have. First, we apply the initial operations and we create num-stack Hourglass modules. Finally, the model outputs multiple heat maps that indicate the likelihood of a joint being located at a specific point in the image. For training, we use ground truth heat maps that highlight the areas where body parts are present. To calculate the loss, we compute the mean squared error element-wise between the predicted heat maps and the target heat maps. So at the end of each Hourglass network, we apply a 1x1 convolution with 16 filters to produce 16 key points heat maps. Another important design consideration is that after each Hourglass, the network generates a set of heat maps similar to the model's final output. This allows us to calculate the loss and apply gradients at each stage. This strategy ensures that the model receives feedback based on the correct labels, enhancing its overall performance. The paper calls this as an intermediate supervision. This is a straightforward Hourglass module consisting of 2 Hourglass networks and 4 steps of downsampling and upsampling. The final paper I will discuss is BlazePose on device real-time body pose tracking. One of the key features of this model is its speed. According to the paper, it can run at over 13 frames per second on a Pixel 2 phone. BlazePose predicts 33 body key points to capture the full body pose. The model's architecture is based on MobileNet v2. The most important design feature in the MobileNet is the use of depth-wise separable convolution instead of a standard convolution. In a standard convolution, a filter is applied across all input channels. For example, if the input has dimensions of h by w by m and we use a filter size of k by k to produce n output channels, the computational cost is h by w by m by k by n. In contrast, a depth-wise separable convolution breaks this process into 2 steps. In depth-wise convolution, a separable filter is applied to each input channel individually, instead of applying a filter to all channels simultaneously. In our example, this results in h by w by m by k computations. Next, a point-wise, one-by-one convolution is applied to combine the outputs of the depth-wise convolution across channels. This step requires h by w by m by n computations. So the total computational cost is this expression. The ratio of the computational cost between depth-wise separable convolution and a standard convolution is then 1 over n plus 1 over k squared. Since MobileNet uses a 3x3 depth-wise convolution, this results in a 1 to 9 times fewer computations compared to a standard convolution. Another important design feature in MobileNet is the use of width and resolution multipliers. These 2 parameters are designed to further optimize the network for lower-end devices by reducing the model size and computational cost. The width multiplier adjusts the number of input and output channels by a factor of alpha, where alpha is a number less than or equal to 1. For example, in the previous example, if the input has m channels and the output has n channels, the width multiplier scales this to alpha times n and alpha times n. Similar to the width multiplier, the resolution multiplier rho reduces the input image dimensions. By scaling the input height and width by rho, the overall computational cost is reduced. In MobileNet v2, we observe several improvements compared to the previous version. The model introduces inverted residual blocks. As I mentioned before, in a typical residual block, the input is first reduced in dimensionality via channels to compress the data, followed by a convolution, and then expanded back to its original size. A skip connection from the input is added to the output. However, in an inverted residual block, the input is first expanded to a higher dimensional space using a one-by-one convolution. Afterward, a depth-wise separable convolution is applied, significantly reducing the number of parameters. The output is then projected back to the original lower dimensional space, and a shortcut is added from the input to the bottleneck layer. Another important change is the use of a linear activation in the bottleneck layer instead of ReLU, as applying ReLU in lower dimensional space can remove important information by zeroing out activations. For instance, as mentioned in this paper, using ReLU on a spiral-shaped input with fewer channels can result in significant loss of valuable input data. For the expansion phase, ReLU 6 is used, which caps the maximum output value at 6, adding non-linearity while controlling the output range. This restriction is useful for mobile applications where computational resources are limited. So, the paper BlazePose builds on these principles of MobileNet and enable fast and accurate pose detection on mobile devices. The model begins with a person detector that identifies areas in the input image when a person is present. Once detected, the model predicts the coordinates of key body parts. The architecture consists of two main components: a heat map-based encoder-decoder network and a regression-based encoder. It starts with an RGB input image, processing it through inverted residual blocks to reduce spatial dimensions while increasing channel depth, capturing essential features. In the heat map branch, a decoder-encoder structure produces heat maps of shape 64 by 64 by 99 with skip connection from the main branch, enhancing accuracy by combining high-level and low-level features. This is followed by the key point regression branch, which reduces the size of the feature map to output 33 by 3, representing the X and Y coordinates and visibility of 33 body key points. During inference, the model omits the heat map branch, optimizing computation for real-time performance, which is crucial for mobile applications. The inverted residual block function creates a residual block with specific input and output channels. In the main branch, the depth of the input is increased while reducing its spatial dimensions. Skip connections are also stored for use in both the heat map and key point regression branches. Next, I implement the heat map branch, where the encoder and decoder map the input to heat maps, incorporating skip connections from the main branch. Finally, in the regression branch, the encoder is implemented to predict 33 body parts coordinates along with visibility scores. To demonstrate BlazePose in action, I utilize the pose estimation algorithm from the MediaPipe library. This library enables the rapid application of AI techniques. MediaPipe pose processes an RGB image and returns pose landmarks for the most prominent person detected. So it provides a single set of landmarks per image. Based on its documentation, I create a pose instance and use the built-in drawing utilities to visualize the result on a copy of the image. For a video stream example, I set static image mode to false, which allows the algorithm to track connections between frames. Thank you for your attention. See you in future.